Hello friends, welcome in lecture of fluid mechanics subject. Myself, Mitesh Patel. I am an assistant professor in a mechanical department at a Dr. Subhash Technical Campus, Junagadh. Today's our lecture topic is a orifice meter. So in this lecture, we have discussion about the what is the orifice meter, what is the application of orifice meter, and equation is derived of orifice meter. Okay, so let's start the lecture. First of all, orifice meter or orifice plate is a device which can measure the discharge of fluid through the pipe. So simply orifice meter is measure the discharge of fluid through the pipe. It's work on the same principle as work the Venturi meter. Okay. So it's work on the same principle in which the work the Venturi meter. It consists of flat circular plate having a circular sharp edge hole concentric with the pipe. So it is a simple plate which having a circular sharp edge hole. This is the orifice meter. This is shown in figure. This hatched section of orifice plate is mentioned in the figure. This is the orifice plate. The diameter of orifice may vary from 0.4 to 0.8 times the diameter of pipe. Okay, but generally the orifice size is 0.5 times the diameter of pipe. Now we can see from the figure that the flow is flowing through the orifice, then the diameter of flow is further decreased after the orifice meter. We can see from the figure. So this tendency of fluid we can know that it's called as a vena contract. So we have considered a two section 1 at a pipe and section 2 at a vena contract to find out the equation of orifice meter. So consider two section 1 at a normal pipe section and section 2 at a vena contract, and manometer, U-tube manometer is connected at a two section as shown in figure. Now A1 is a area of pipe, cross section area of pipe at a section 1, and V1 is a velocity of fluid at a section 1, and P1 is a pressure at a section 1. Similarly, A2 V2 cross section area at a vena contract or section 2, V2 is a velocity of fluid at a section 2, and P2 is a pressure at a section 2. Okay. Now we applying the Bernoulli's principle at a section 1 and section 2. So we know that in Bernoulli's principle, three energies considered: pressure energy, kinetic energy, and potential energy. So all three energy summation at a section 1 and section 2. We know that the orifice meter is horizontal, so potential energy difference Z1 minus Z2 is 0 because Z1 is equal to Z2. Datum height is not different at both section because pipe is horizontal, so potential energy difference is 0. So potential energy value is not affect in this equation or any other value. Okay. Now we have to find the H. What is the H? We know that the pressure head difference is denoted as a H. Pressure head difference P1 rho g minus P2 rho g is known as a H. This is a pressure head difference, and Z value we know that not affect any value. So H, we write the H instead of pressure head difference. So in this relation or Bernoulli's equation, H is equal to V2 square upon 2G minus V1 square upon 2G. And now 2GH is equal to V2 square minus V1 square. From this equation, we have to get the value of V2. So V2 equal to under root 2gs plus V1 square. Under root is due to the V2 square. The square is removed from left and right side. So right side value is in under root. Okay. Now CC, the coefficient of contraction, we know that it is the ratio of A2 upon A0. What is the A2? A2 represents the cross section area of vena contract, and A0 or AO is a cross section area of orifice. Okay. So coefficient of contraction is a ratio of area of vena contract to area of orifice. Okay. So from this relation we can find out the value of A2. So A2 is equal to A0 into CC, coefficient of contraction. Okay. This is the denoted by equation 1, and this equation is denoted by equation 2. Now applying the continuity equation at section 1 and section 2, so A1 V1 is equal to A2 V2. From this relation we find out the value of V1. This is the V1 is equal to A2 upon A1 into V2. Now value of A2 take from this equation, then equation is V2 is equal to A0cc upon A1 into V2. Okay. Value of A2 is put from this equation. Now value of V1 from the continuity equation we have find out, this is placed in this equation of V2. Okay. Now V2 square, in this equation the square of the OR element in left and right side, so under root is removed from right side and V2 is squared. Okay. Now rearrange the equation as shown in slide and find the value of V2 or equation of V2 from this relation in this way. So V2 is equal to under root 2gh upon under root 1 minus A0 upon A1 square CC square. Okay. Then discharge. We know that the equation of discharge, velocity into area. So here discharge is equal to V2 into A2. Now put the value of V2 and A2 from the equation 1 and 2. A2 value is equation value is a A0 cc. Okay. So here V2 into A0 cc. Now value of V2 is placed from this equation. So now equation is a Q is equal to A0 cc under root 2gh upon under root 1 minus A0 upon A1 square CC square. Okay. Now experimentally proven that CC and CD relations as shown in slide, CC upon under root 1 minus CC square in bracket A0 upon A1 square equal to CD upon under root 1 minus A0 upon A1 ratio square. This is the relation of CC and CD. Coefficient of contraction and coefficient of discharge is experimentally proven, is directly given through the experimental. So we can find the equation of coefficient of contraction from this relation in the form of coefficient of discharge. Okay. So find the value of or equation of CC in form of coefficient of contraction equation in form of coefficient of discharge. Okay, as shown in slide. CC is equal to CD under root 1 minus A0 upon A1 square CC square upon under root 1 minus A0 upon A1 square. Okay. Now the value of Cc put into the equation of discharge, equation of 5. So equation become as shown in slide. And now in this equation, this value or element is cancelled, similar so remaining element is a CD A0 under root 2GH upon under root 1 minus A0 upon A1 square. And now rearrange the equation in this form. Q is equal to CD A0 A1 under root 2GH upon under root A1 square minus A0 square. Okay. And CD is, we know that, coefficient of discharge for orifice meter. Okay. And this is the equation of discharge through orifice meter. This is the discharge equation of orifice. This is the final equation of discharge for an orifice meter. Okay. Now we solve the example of orifice meter. So first example is start to solve. An orifice meter with orifice diameter 10 centimeter is inserted in the pipe of 20 centimeter diameter. The pipe diameter is 20 centimeter, that is a D1, and orifice diameter, we know that, denoted by D0. The pressure gauge is fitted, manometer is not used, but here pressure gauge is fitted. Upstream and downstream of the orifice meter gives a reading of 19.62 Newton per centimeter square and 9.81 Newton per centimeter respectively. So it is a P1 pressure and P2 pressure is given, okay, in this data. The coefficient of discharge for the orifice meter is given as a 0.6 and find the discharge of water through the pipe. The CD value is given 0.6 and we have to find out the value of discharge through the pipe. Okay. So now we solve the, first of all write the all datas and then we find out the discharge. So first of all we have to find out the discharge. We know that the equation of discharge for orifice meter. So we have to find out all elements of this equation. Cross section area at a vena contract, orifice meter, and cross section area at a pipe, and H, value of H. This is the difference of pressure head. So we have to find out the three value: cross section area of orifice meter, cross section area of pipe, and the pressure head difference. Okay. So P1 upon rho g, we have to first find out the value, and P1 is given in Newton per centimeter square, that is converted into the Newton per meter square, so is multiplied by 10 raised to 4. And rho, density of water, we know that 1000, and G is a 9.81. So we have to find out the value of P1 upon rho g, and then after we find out the value of P2 upon rho g. So P2 is given 9.81 Newton per centimeter square, that also is converted into the Newton per meter square. Density of water is 1000 and value of G is a 9.81. So final value of pressure head at a P2 due to P2, so that is a 10 meter of water. Okay. So now get the value of H. Take a difference of pressure head and finally we have find out the value of pressure head in form of water head, 10 meter water head or 10 meter column height. Okay. Now value of coefficient of discharge for orifice meter is a 0.6. Okay. Now value of all elements put into the equation, and we have find out the finally value of discharge in form of centimeters cube per second, and this into convert into the liters per second. Okay. Now take another example of orifice meter. An orifice meter with orifice diameter 15 centimeter is inserted into the pipe of 30 centimeter diameter. Pipe diameter is given 15 centimeter and the orifice diameter is 15 centimeter. Sorry, the 15 centimeter diameter is a orifice diameter and 30 centimeter is a pipe diameter. Okay. The pressure difference measured by mercury oil differential manometer. Here manometer is used. The two side of the orifice meter is given as a reading of 50 centimeter of mercury. So mercury column difference reading is a 50 centimeter. So it's a value of x is a 50 centimeter. Okay. Find the rate of flow of oil of specific gravity 0.9 meter. The flow of fluid is a oil and its specific gravity is a 0.9 is given. Okay. Now the coefficient of discharge of orifice meter CD, value of CD is given 0.64. Okay. Now let's start the solution of example or problem. So we have to find out the discharge through the orifice meter. So we have to use the equation of discharge for a orifice meter. So first of all, we have to find out the cross section area at a orifice meter, cross section area at a A1 at a cross section area at a pipe, and we have to find out the H, value of H. H is a pressure head difference. So first of all, we have a diameter of our orifice meter. So we have to first find out the area of orifice meter. Then we have a diameter of pipe. So we have to find out the cross section area of pipe. Now the manometer is used. So we have an equation for a manometer to find out the value of H. So equation is a H is equal to x into Sg upon S0 minus 1. Here Sg is a specific gravity of flowing liquid through the orifice meter and SO is a Sd is a specific gravity of the heavy liquid which are used into the manometer. Here the heavy liquid is a mercury and SO is a specific gravity of flowing liquid through the orifice. Okay, so it's a oil which are flow into the orifice meter or pipe. So its specific gravity is a 0.9, SO is a 0.9, and we know that the mercury specific gravity 13.6, and we have a value of x in form of centimeter 50 centimeter. So we have a value of H in form of centimeter 705.5 centimeter column of oil. H is a. So now we have all the value of all elements in discharge equation. So put the value of all elements in this equation and we have finally find out the value of discharge 137414.24. Okay, this is the answer in centimeter cube per second and this convert into the liter per second. Okay, so now I hope you understand very well all things about the orifice meter. What is the orifice meter? What is the perfect application of orifice meter? And how the example is solved of orifice meter? And how the find the discharge through the orifice meter? Okay. If you have any question, feel to free ask to me. Okay. Thank you.